Hi everyone, I hope you guys are having a wonderful day. So this video is about the Euler path and circuit theorem, and I'm going to show you how to prove it. But if you are going to do the Euler path and circuit theorem project, please make sure you finish that project before you watch this video, because this video basically gives the answer, and the project is all about kind of discovering for yourself why this theorem works. So if you're choosing to do that project, please make sure you finish that project before you watch this video. So if you have finished that project, or if you decided you didn't want to do that project to get those points, you can go ahead and keep watching. And let's go ahead and take 3 deep breaths and make this math easy. All right, so in the Bridges of Königsberg assignment, you guys were asked to figure out if it was possible to go on a walk through the streets of Königsberg and cross each bridge exactly once and end up back where you started. And in that video, we talked about how that question can be simplified to a graph theory question, where the vertices represent the different land masses in the city, and the edges represent the bridges that cross over the river to get to those different land masses. So in that assignment, you must have discovered that it is not possible to go on a walk through the city and cross each bridge exactly once. And the reason why it doesn't work is because of the number of bridges that are leaving each landmass. So if you remember, the degree of a vertex is basically the number of edges that are leaving it, or the number of vertices that are adjacent to it. So the degree of the north bank vertex would be 3, because there are 3 edges leaving it, or 3 vertices that are adjacent to it. Because this vertex kind of counts like twice, because there's 2 edges that go to it. So the degree of the north bank would be 3, the degree of the east bank is 3, and the degree of the island is 5, and the degree of the south bank is 3. And so essentially those numbers are describing how many bridges leave that landmass. And if you think about it, let's say maybe I started walking on the island. Well, if I have 5 bridges and I want to only cross each bridge exactly once, then it will be impossible for me to get back to the island at the end of my circuit because I have an odd number of bridges. And the reason this doesn't work is because let's say I started on the island. Well, if there's only 5 bridges that are attached to the island, they kind of have to go in pairs, because if I leave the island, I need to be able to get back to it. And so, I could leave the island and then come back here. I could leave the island and come back here. But then once I leave the island, there's no bridge to bring me back to the island. And the question I was asking is it possible to go on a walk through the city and cross each bridge exactly once and end up back where I started? But it's impossible to do that because the island has an odd number of bridges. And actually, all of the other land masses also have an odd number, so they would have the exact same issue. And so this is the reasoning behind what we call the Euler path and circuit theorem. So the Euler path and circuit theorem says that a graph will contain an Euler circuit if it is connected, because you have to be able to get to all of the vertices. So if it's not connected, that wouldn't work. And if all of the vertices have an even degree. So that's the Euler circuit theorem. And basically the reason all of the vertices have to have an even degree is because you need to be able to go into the vertex and leave it in order to have a circuit. And then the path theorem is very similar, where it says a graph will contain an Euler path if it is connected and there are at most 2 vertices with an odd degree. Because with a path, you don't necessarily have to start and end in the same spot. You can, like it is possible to have paths where you start and end in the same spot, but you don't have to. And so if you want to have an Euler path, then you could have 2 vertices that have an odd degree, and those would just be your starting and ending points. So for example, if we look at this graph, the degree of vertex A is 2, the degree of vertex C is 3, the degree of D is 2, and the degree of B is 3. And so let's say that I start my path at B. Well, I can go in and out of D, and then I can go in and out of A, and I can end at vertex C. So if I have 2 vertices with an odd degree, then I could do a path, but it won't be a circuit because I didn't end up back where I started. Because the 2 vertices with the odd degree either have to be the beginning or the ending point of my path. So when you write a proof for this, and hopefully you've already finished it if you decided to do the Euler path and circuit theorem project, the way that you write a proof is you basically kind of rephrase the theorem in an if-then statement. So for example, in the circuit theorem, we would say if your graph is connected and all of the vertices have an even degree, and you'd like actually write this out nicer, but basically you say like if those 2 conditions are met, if your graph is connected and all the vertices have even degrees, then an Euler circuit exists. That would kind of be the way you would rephrase it as an if-then statement. And then you would say, okay, well, the way that you prove this is you assume that the if statement is true. So you say like, okay, well, if I have a connected graph that has all vertices with an even degree, then you use that assumption to prove that the then statement is true. So an example of this is a proof that I wrote for the Euler path and circuit theorem. I start off by saying, suppose that I was given a connected graph where all the vertices have an even degree. So this sentence is where I'm kind of assuming my if statement. So I say, if I have a connected graph where all the vertices have an even degree, then I go into my proof to explain why an Euler circuit does exist. So I say this graph will have an Euler circuit because I can choose any vertex as my starting point. And because the graph is connected and all vertices have an even degree, the starting vertex and all of the other vertices will have a degree of at least 2. Because my assumption was that all vertices have an even degree, which means it's either 0, 2, 4, 6, 8, etc. But because the graph is connected, that means that all the vertices have at least one edge attaching it. And so that means that none of the vertices have 0 degree. And so I'm saying, okay, well, I know that all of the vertices are going to have a degree of at least 2. And so because this starting vertex has a degree 2, when I leave the starting vertex, I will be able to get back to it at the end of the circuit. If it has a degree of like 4 or 6 or 8, I might go into it and leave it multiple times throughout my circuit, but because it's at least 2, I will be able to get back to that vertex at the end of the circuit. And since every other vertex has an even degree as well, every time I enter a vertex, I will be able to leave it by a different edge than the one that I used to enter it. And because the graph is connected, I'll be able to visit all the vertices and cover all of the edges that are attached to them. And so this is my proof that the graph will have an Euler circuit. So again, the structure is kind of you assume your if statement. So I say, suppose I was given any connected graph where the vertices all have an even degree. Then I just talk through my reasoning of why those 2 assumptions means that I will definitely have an Euler circuit. So this is an example of my proof. And on your Euler path and circuit assignment, you're going to be given a ton of different graphs, and you're going to determine with the Euler path and circuit theorem if it's possible to draw an Euler path or circuit. And you'll also be using Fleury's algorithm. to actually find those paths and circuits. But the path and circuit theorem is a key part of that, because if a path or circuit doesn't exist, and it's impossible to do it, then you don't want to try to draw one because it just won't be possible. So for example, on this graph, if you wanted to find out if it was possible to draw a circuit or a theorem, a circuit or a path, then you would basically just go through and calculate the degree of each one. So you would say, okay, well, the degree of this vertex is 2, the degree of this is 2, this is 4 because there's 4 edges leaving it. This one is 4, this is 2, 4, 2, and 4. And so because they're all even degrees, then by the Euler path and circuit theorem, that means that the graph does contain an Euler circuit. So if you have any questions, let me know, and I hope you guys have a good day.